Let me start by introducing our speaker today. Welcome to the Combinatorics seminar. And today we're very happy to have Jacob Matherne from University of Oregon. He's going to talk about singular Hodge theory for combinatorial geometries.
Yeah, thank you, Lei. Actually, I'm not able to share my screen.
Oh, okay. We should take care of that first.
Okay, you can see this blank sheet?
Yes.
Okay, so I'm just gonna go for it. All right, so I'll talk for around 30 minutes. My plan for this pre-seminar is just to give some definitions and do some examples for sort of objects that I will use in the main talk. So the first thing I want to do is sort of give the definition of a metroid that I'm going to use. I think everyone gets flack when they give these talks for not giving a definition of a metroid, but okay, so I'll do it now. But before then, I just want to say sort of, a lot of places where metroids come up. So can people see my writing? Yeah? Okay. So metroids, they arise from lots of different objects. So for us, in sort of the main talk, hyperplane arrangements is going to be the most important one. But they also come from graphs, and sort of the definition is inspired by vectors in a vector space. And all of these different settings all have some notion of independence or dependence, and the idea of a metroid captures this independence or dependence in all of these different settings. Okay, so let me give you the definition of a metroid that I want to use. So there are many different definitions of a metroid. They're all equivalent, and depending on which object you're thinking about, some are more convenient than others. So a metroid M on a finite set E. So I have this finite set, and a metroid is going to be a collection of subsets of that finite set, satisfying some properties. So it's a non-empty collection of subsets of E, satisfying some properties. So my subsets are going to be called flats. So all the definitions of metroids are like you have some subsets satisfying some properties, but my subsets are going to be called flats. And here's the properties that they're going to satisfy. So if I have two subsets, two flats, F1 and F2, then the intersection must also be a flat. So it's closed under taking intersection. And for every flat F and every element I so if I take the whole set E and I subtract my flat and I pick an element in E minus F, then this is in exactly one flat. And I'll do a bunch of examples because I know this definition is not easy to comprehend at the beginning. One flat that is minimal among flats strictly containing F. Okay, so this is what a metroid is, but I'm also going to assume one more thing. So I'm going to assume that the empty set is a flat, the empty subset. This means that M is a loopless metroid. This is just something I need for convenience. I don't really need it, but it's nice. Okay, so here's some definition. It's okay if this doesn't mean anything to you. I'm going to do some examples, okay? So before I do an example, I want to tell you that if you have this collection of subsets called flats, then they form a ranked lattice. They have a nice structure. So these flats, together, they form a ranked lattice. And this is called the lattice of flats. And I'll denote it L of M. Okay, so now let's do an example. Yeah.
Jacob, I think there's a question in the chat.
Okay. Let's see.
Vasily, can you repeat your question? I think, yeah.
Yeah, when you write strictly containing, do you mean just containing?
I mean strictly, yeah, I mean like so in this lattice, it should be a cover. This is what I mean. Yeah, I mean, and Alex is correct. It doesn't matter. Yeah.
Okay.
Yeah, please ask more questions. Okay, so this I'm going to call Boo3. It's the Boolean matroid of rank 3. So what this is the set of all subsets of the numbers 1, 2, and 3. Okay, so I have the set of numbers 1, 2, 3, and I want to look at all subsets of it. So I have the empty subset, and I'm going to be lazy and not write the braces for the subsets, but I have the subset containing 1, the subset containing 2, the subset containing 3, these singletons. I have 2-element subsets, and then I have the whole set. Okay, so this Boolean lattice, this Boolean matroid is going to have its lattice of flats looking like this, the set of all subsets. And what is the relation here? So it's ordered by containment. So the empty set is contained in all of these singletons. The singleton 1 is contained inside of these 2 pairs, and so on. So I can fill this in. Oops. 3. Yep. Okay. And then here, here, and here. Okay. So this okay with everybody? And it's a ranked lattice. Okay. And rank is just this is rank 0, this is rank 1, this is rank 2, this is rank 3. So rank is a maximal chain of flats starting from the bottom. How high you have to go up starting from the bottom. Okay. So that's one example. Let me do one more example. So this next one is called the uniform matroid of rank 3 on 4 elements. So I say the notation's kind of funny here, but I'm trying to match someone else's paper who wrote the sort of first paper on this. So this is rank 3, so uniform of rank 3. So this is rank. And the sum of these is the number of elements. In this set E, which is the top flat. Okay, so this is E. Okay, so what does this look like? So what I do is I start with the empty flat, and then I have the singletons, and I keep going up until my subsets are size 1 less than the rank. So the rank here is 3, so I'm going to have these pairs. And I keep going up until I'm one less than the rank, and then I jump all the way to the top. So there's a jump. I don't have the triples here. Okay. And then again, it's just containment of subsets, the relation. So you can draw all of these in. It gets a little bit cluttered, but here they are. Okay, so here are 2 examples of matroids. You should just think of a matroid for the purpose of this talk as a lattice satisfying these properties. Okay. And I want to say that both of these are members of a family, as I said before, so they're families. So I could take the Boolean matroid on n elements. So the set of all so the flat is a subset of the set 1 through n. And then I could take uniform matroid of rank D on m plus d elements. So again, I start with the empty flat. I take all subsets up to size d minus 1. and then I jump to the top. Okay. Okay, so in my main talk, I'm going to talk about two conjectures about metroids. So the first conjecture is about the shape of this lattice of flats. So here is what it says. It's called the top-heavy conjecture. It says that if I draw a horizontal line through the middle of this lattice of flats, so here I draw a horizontal line through the middle of this lattice of flats, then the top-heavy conjecture says that if I start at the, let me use this thing. So if I start at the bottom and I go up some number of levels, so, but I don't cross this line. And then I start at the top and I go down the same number of levels, then there are more elements at the top level than the bottom. Okay, so let me try to explain. So in this first Boolean example, I could compare this to this. So there's one element at the top and one element in the complementary rank. Okay, and the top-heavy conjecture says that the top one is greater than or equal to one. Okay, and then this is, I can compare one down and one up. So I also have 3 greater than or equal to 3. So for these Boolean metroids, it's not so interesting. They're completely symmetric. Okay, but for the uniform metroid, I could compare this one to this one, and also this one to this one. And these two give me 1 greater than or equal to 1. And then these two give me 6 greater than or equal to 4. So the top-heavy conjecture says in complementary degrees, you always have more things on the top than in the complementary degree on the bottom. Okay.
So this top-heavy conjecture, what metroids is it for? What classes of metroids is it for? Is it for all metroids?
It's for all metroids. Yep.
Oh, okay.
Yep.
Yeah, because it seems obvious for the two families that you've written here, but if it's for all of them, sure, yeah.
Mm-hmm. Yeah, it's for all metroids. That's true. Yep. Yeah, so I'll say a little bit of the history in the main talk, but if you're familiar, so now I'll just since you asked the question, so are you familiar with the notion of representable or realizable metroid, Alex?
Yes, sort of. I could tell you the definition, but I don't know much about them.
Okay, so I mean, in my main talk, it's going to turn out that, I mean, realizable metroids are ones where you can associate all sorts of algebraic geometry to. I mean, you have a hyperplane arrangement, so you can build some kind of variety out of this hyperplane arrangement. And it turns out that this top-heavy conjecture has a very beautiful proof using algebraic geometry for realizable metroids. And in my main talk, I'm going to explain how do you emulate that proof if you don't have geometry?
Wait, sorry, I know what representable means. Is realizable just another name for the same thing?
Yeah, same thing. Yep.
I see, thank you.
Mm-hmm. Yep. Okay. So this is the top-heavy conjecture, and I want to, in the 15 minutes that remain, I want to talk about the other conjecture, which has to do with these polynomials called Kazhdan Lusztig polynomials. So maybe I'll just spend the last 15 minutes talking about what Kazhdan Lusztig polynomials are and trying to give you a feel for them. So first, let me talk about 2 ways to get new metroids from old ones. So I could do this thing called localization. So for any flat f in the lattice of flats of a metroid, I can build 2 new metroids. So I can do localization at the flat f. So what this means is I take the interval below the flat f. Okay, so I find my flat f inside of my lattice of flats, and I just take everything below it. And this is going to be the lattice of flats of a new metroid, okay, called the localization. And then there's one called contraction. Contraction of f. So And I'm gonna write this one, this localization, as M super F to sort of mean, you know, I'm taking everything below F. And I'm gonna write it like this for the contraction. And this is sort of the opposite thing. So I take the upper interval. Okay, and these are both new metroids.
Is localization the same as deletion of the complement of F?
Yeah, that's right. Yep. Yeah, in fact, if you try to use Sage, you know, we're in the metroid package in Sage, they have one of them, but not the other one. So you do exactly what you said to do the other one.
And for both of these, we have to modify the ground set, it seems.
Yeah, that's right. Yeah, so I'm leaving out a few details, but you're right. The localization, the ground set is now the elements of the flat F.
Right.
Yeah, and for the contraction, you do the ground set minus F is the new ground set. Yeah.
Because the elements of F are in everything.
Yep. That's right. Yep. So good. So here's a definition. Yeah, please ask if anything is not clear. I'm like not writing everything, but I'm expecting you to ask questions. So here's this thing called the characteristic polynomial of a metroid. So what this is, I'll define it, and I'll give you sort of an easier to remember definition in my talk, my main talk. So I sum over all of the flats in the lattice of flats. And then I have some value of the Mobius function. Okay, I'll explain this in a bit. Times t to the corank of F. So corank is the rank minus the rank of the metroid minus the rank of the flat. And again, rank is the size of a maximal chain of proper flats. Okay, so the rank of the metroid in the first example is 3, and the next example is 3. So both of these examples are rank 3 metroids. Okay. So let's compute the characteristic polynomial in this uniform metroid. So I'll copy it. So this is our second example. Okay, so let me first write the coranks. So corank is 0, 1, 2, 3. Okay. And then let me tell you what this Mobius function is. Okay. So what it is it's the unique integer valued function that takes the value 1 at the bottom of the poset, and its value at any other flat is such that the sum of that value and everything below it is 0. L of M is the lattice of flats of the metroid, so it's just the poset that I've been looking at. So yeah, so I want to give values to each of these flats so that the sum of the values of it and everything below it sum to 0. Okay, so this should be -1, right? Because I have this plus this below it has to be 0. And same with all of these. So I'm writing down what this mu is. Okay. And then now if I'm at 1, 2 here, so if I'm at 1, 2, I have 1, 2, and the empty flat. Okay, so I have to do -1 plus -1 plus 1, right? And then I have to put something here to sum it to 0, right? Okay, so I keep doing that. And then finally, if I'm at the top flat, I have to look everywhere below it. And if you sum all of these numbers, you'll see that you have to put -3 here. Okay. so the characteristic polynomial of the metroid in this case, so I put all of these numbers, and what I have to do now is just multiply by t to the corank. Okay. So good. So starting at the bottom, I have t cubed, right? And then in the next level here, this is my t squared stuff. So I have negative 4t squared. And then this is my t stuff. So I have plus 6t and then minus 3. Okay. So this is the characteristic polynomial. Okay, so let me give you the definition of the Kazhdan Lusztig polynomial, which will be one of the main topics of my main talk. So this is a definition / theorem. So I'll explain what that means. But it was defined in a paper by Elias, Proudfoot, and Wakefield in 2016. So the existence of such polynomials is the theorem part, okay? So there exists a unique way to assign to each metroid a polynomial with integer coefficients. I'll call this polynomial PMT. So this is called the Kazhdan Lusztig polynomial of a metroid. Satisfying the following things. Okay. So first property is that if the rank of the metroid is 0, then I assign the polynomial 1. Second property, if the rank of the metroid is positive, then there's a degree bound on this polynomial. So the degree of the polynomial is strictly less than 1/2 the rank of the metroid. And the third property is some recursion that helps us to define the polynomials in terms of polynomials for smaller metroids. Okay. So it says that t to the rank of the metroid, PMT inverse, is equal to the sum over all the f in the lattice of flats, the characteristic polynomial for the lower interval, everything below f, times the Kazhdan Lusztig polynomial for everything above f. Okay. So it's a crazy definition. If you've seen Kazhdan Lusztig, classical Kazhdan Lusztig theory for Weil groups and Schubert varieties and stuff like this, this is analogous, but in a different setting. I'll talk more about that in my main talk. But since I have 5 minutes left, let me tell you sort of, in these examples, what do you get that I've shown before, and some properties of these Kazhdan Lusztig polynomials and what is known about them. Okay. So the constant coefficient is always 1.
So I noticed that the expression on the right contains the polynomial itself when you set f to be the empty set.
Yeah. So you definitely need number 2. So this degree bound is very important, or else you can't solve the equation. That's right. Okay. Yeah, good eye. Yeah. Yeah. Cool. Yeah, and the coefficient of t, so the linear coefficient, this is the number of flats of co-rank 1 minus the number of flats of rank 1. So I'll use this notation. So if I put a superscript, it's the flats at that rank. So the number of flats of co-rank 1. So maybe so rank of m minus 1 minus the number of flats of rank 1. Okay. And then afterwards, all coefficients have some kind of interpretation in terms of things called flag Whitney numbers. So it's like you tell me an increasing chain of numbers between 0 and the rank of the metroid. And then I give you all flats, all chains of flats with those ranks. And all coefficients can be written as sort of linear combinations of such things. So it becomes extremely complicated. And one big conjecture, which is now a theorem, which I'll talk about in the main talk, is that the coefficients of these polynomials are non-negative. And from this description, it's completely unclear why it should be non-negative. So we have to really use some geometry. Okay, so in the last 3 minutes, I think what I'll do is I'll just show you some tables of polynomials and ask you if you see some properties, okay? So let me stop this share and share something else. 1 minute. Okay. You cannot share something if it's minimized. Okay, now I know. Okay, so here's the original paper where this Elias, Proudfoot, Wakefield paper where these Kazhdan Lusztig polynomials of metroids are defined. So I'd like to just, there are some tables at the end where they compute a lot of these metroids. So this family here, this M1D, this uniform metroid of rank 3 on 4 elements lives inside of here, inside of this family. And it's this one. So the way you should read this table is that this is the value of D along this row, and the polynomials are read vertically. So if D is 1, if the rank is 1, this is the polynomial is 1, 1. If the rank is 3, it's 1 plus 2t, 1 plus 5t, 1 plus 9t plus 5t squared, and so on. So maybe I can ask for observations in the last minute. What do you notice about these polynomials reading vertically along the columns? Anything?
The lengths skip by 2. They're the same in pairs.
Sorry, I couldn't hear you, Sarah.
The lengths come in pairs.
The degrees are maximal according to that condition too.
Mm-hmm.
Yep. Okay. Yeah. So most, right. Most of these polynomials get to half. That's right, to half degree, which is not like the classical Kazhdan Lusztig polynomials.
Coefficients seem to be top heavy.
Yeah, like unimodal, right? Or sort of, yeah. So they are right, top heavy.
They do vaguely resemble binary coefficients in some way.
You mean the middle is? I mean the peak is sort of like not quite in the middle, but it's sort of farther.
Well, yeah, I'm looking at for example, let's see, t comma for t equals for in degree 1, if you look at D, if you look at the dependence on D, it's D times D minus 1. Sorry, it's D minus 1. No, it's D times D minus 1 over 2 minus 1. Triangle numbers minus 1.
Yeah.
So
excellent.
it's quadratic, and I'm guessing it's of degree n minus 1 in general.
Yeah. So I mean, not too much is well. There's a formula for these. I mean, so for the uniform ones, I think there's a formula. I'd have to look at the formula to see what you're saying is correct. Yeah, so let me just mouth off really quick and then I'll stop. So the coefficients are non-negative. I'll talk about this in the main talk. It's a conjecture that these polynomials are real rooted. This is still not solved. It's known for some classes of metroids, but not in general, by far not in general. It's not even known for all uniform. It's known for some values of uniform because a computer was used to check things. Yeah, and yeah, I think I'll stop there since I'm 1 minute over time. Yep.
Thank you. Let's all thank the speakers first.
Thanks.
Any questions from the audience?
I didn't see Leopold's message in the chat. Yes, they seem unimodal, but that's also not proven, but it's conjecture. Yeah.
Are you
Last
going to
question.
talk about significance of this polynomial in your main talk?
Yeah, absolutely. Yeah, so I don't know if you're familiar with the classical Kazhdan Lusztig theory, but they have a similar geometric interpretation. They're like, you know, intersection cohomology Poincare polynomials of some variety.
They mean, do they say anything about metroids or non-realizable case? But if you understand, let's say, all these conjectures about coefficients, can you unravel something deep about metroids?
It's an interesting question. Yeah, we sort of went the other way. I mean, we were just trying to solve this non-negativity conjecture for, you know, like the coefficients were non-negative. I mean, it's a long story. So, I mean, about the metroid itself, I'm not quite sure. I mean, the top-heavy conjecture is something nice about the metroid itself, but the conjecture about the non-negativity of these polynomials, I'm not sure what it says about the metroid. But as you'll see in the talk, what we do is we develop something called the intersection cohomology of a metroid. So we develop some kind of cohomology theory of a metroid. And what this says, I mean, we interpret these Kazhdan Lusztig polynomials as Poincare polynomials of this intersection cohomology. So this is a roundabout answer, but one thing you could say is that if you were interested in what is the intersection cohomology of a metroid, I mean, this is some new invariant of a metroid, and the Kazhdan Lusztig polynomials sort of control the behavior of this new invariant. Yeah, but nothing simple that I know to say.
Thanks.
Yeah, Sarah?
Did you come up with any, in the example that you had there, the first one, it kind of looks like the numbers factor a lot. So 32 has only prime factors 2, 7, 11, and 13. Did
Okay,
you
let me
look for
bring
factored formulas at all?
Okay, right. So I don't think things generally factor. I haven't looked at this that much, but I do know that there is I mean, I was working on you know, something long. I mean, I've been working on this for 3 or 4 years now, and in some shared document, there's some note that Nick Proudfoot wrote that says Sarah suggests we factor these polynomials.
Oh no, so, I'm repeating myself.
So I'm sure
different actually.
Okay.
Actually, that note is about factoring the polynomials over this particular form of factorization where you try to find the factors that are what I call pretty factors, 1 + q squared, ... up to q to the k for some k.
Okay.
Like the q analog of the number k.
Yeah. Okay. So what? Say what you're, because that's just what I had in mind. Say what you mean again here.
Well, actually, the coefficients just in this table, do they have any special properties individually? I mean, wouldn't it be so nice if you could say what the kth coefficient is for a particular d?
Yeah.
You know,
so
like hook length formula fashion.
Right. Yes. So it's a great question. Yeah. So in fact, yeah, there's an exact answer in this in terms of representations of the symmetric group. So let me explain. So there's another thing you can do. You can consider.
Oh, well, actually, are you going to talk about it in your talk?
No.
Oh,
it's
okay, good.
Like a tangential story. Yeah.
Okay.
So there's a notion of equivariant Kazhdan Lusztig polynomial. So what I do is I have you know, take a finite group that acts on the ground set of my metroid, such that it sends flats to flats. This is a symmetry of the metroid, and if you do this, you can define, you know, Kazhdan Lusztig polynomial, equivariant Kazhdan Lusztig polynomial by carrying this group action through. And it turns out that the coefficients now are representations of the group that's acting. And if you take the dimension of those representations, you get the Kazhdan Lusztig polynomials that I'm talking about. And for the uniform metroid, the first formula for what these polynomials were was found like that, because it was sort of like with a lot of computer evidence, you couldn't really come up with a nice formula. But once you work equivariantly, you can see which representations are appearing, and then you can prove the formula. So it's exactly some kind of thing like that.
Yeah.
Mm-hmm.
Where do you, maybe while we take our little break, would you put something in the chat about
Sure.
reference for that?
Yeah, absolutely.
Or if you need a break too, we can do it afterwards.
I'll just get some water really quick, and then I should have time to do both things. Yep. Okay,
cool.
I'll be right back.
Well, we're thanking you one more time.
Oh, thank you.
I guess we have
Okay,
a 3 minutes break.
let's call it 5.
Okay,
Okay.
that's good.
While we're talking about coefficients of those polynomials, it looked like for the prime columns, the leading coefficient was divisible by that prime, except for 2 and 3. I mean, so I guess
That's interesting. That might come out of the representation theory side. Yeah.
I was also briefly looking at like the sum of the coefficients, and it looked like some of the coefficients seem to increase by like almost every other Fibonacci number.
That would be a neat pattern too. Well, you got 4 more minutes to figure it out.
It looked like in the top table there were the Catalan numbers showing up along the diagonal.
Yeah, that's right. Some there are some special cases that are Catalan numbers. That's right.
Yeah, I was talking about how they seem to be related to the binary coefficients. Like the first row was triangle numbers -1.
Nice.
Yeah, I think the Catalan numbers would fit with Alex, with your guess about the degrees, right? Like the degree being 2n. Although maybe that's a different limit you're looking at.
Yeah, so this is the.
Where exactly did you see the Catalan numbers appearing?
Yeah, I don't know. I mean, I haven't looked for that. But I think I would guess that it's pretty rare. I mean, sort of there are tons and tons of metroids, and I know that the Kazhdan Lusztig polynomials get incredibly complicated. So I would guess that it's pretty rare. So in this article that I linked, so this is what I was talking to Sarah about when she asked about representations of the symmetric group. So this is a paper that explains how you could let the symmetric group, or whatever finite group acts, act on the ground set, on this E set of the metroid, and such that it sends flats to flats. And then if you define everything appropriately, carrying this group action around, then you get a notion of equivariant Kazhdan Lusztig polynomial. And theorem 3.1, yeah, you guys are noticing all sorts of nice things. It's cool. So theorem 3.1 is the theorem that gives the coefficient, the ith coefficient of the uniform metroid of rank D on m plus D elements in terms of representations of the symmetric group on m plus D elements.
Jacob, I'm sorry to interrupt, but we should probably start the main seminar.
Okay, yeah, sure. No problem.
Would you like to share the screen?
Yes.
And meanwhile, I can make some introductions.